Hello, physics friends. We're going to talk about EMFs today. This is the first in probably 3 or 4 installments from our circuits chapter. So I'd like you to take a moment, please pause the video, and I'd like you to answer these these two questions. What is an EMF, and what is the difference between a real EMF and an ideal EMF? So an EMF, the word EMF stands for electromotive force, and the words really tell us it's an electric force that's moving charge, right? It's kind of an old term, so we don't spell it out too often. We shorthanded EMF. And its purpose really is it provides a potential difference. It's a supplier of energy to a circuit. It pushes or pumps the charge. We often talk about EMFs in short for an EMF device. So it is some sort of device or thing that is providing the potential difference or supplies the energy. So that EMF is some EMF devices would be batteries, generators. We're going to spend most of our time talking about batteries because we're studying direct current circuits, and that is the most common way or common device that provides that potential difference within a circuit. The EMF in a physics definition is given to us as curly QE, right? Curly QE is equal to the work per unit charge, and it basically moves the charge uphill. So its purpose is to take that charge and move it up the hill, up to the high potential. It does that through work. And if we look at the units, it should make a little bit of sense to us. So our unit for our work would be a joule, and the unit for charge is a coulomb, and we know a joule per coulomb, or energy per unit charge, is also known as a volt, which is consistent with this idea that an EMF provides the potential difference or that push for the charge around the circuit. Then the next idea that we need to distinguish is between the difference between a real EMF and an ideal EMF. So this picture you see here is a battery overlaid on top of what's actually kind of going on inside in terms of a schematic diagram. So we have the EMF that's shown here, that's that little guy there. That would be considered like an ideal EMF. It has the ability to produce a given amount of potential difference. And then this resistor here, this is its internal resistance. So a real EMF is going to have internal resistance, where an ideal EMF would not have any internal resistance. What's important about an EMF and the difference between a real and ideal is the difference between its terminal voltage. So if we were to take a voltmeter and measure the terminal voltage of battery, a real EMF would have a difference between the terminal voltage and then that EMF due to the internal resistance. An ideal would have no difference between those. You can't really tell the difference between an ideal and a real EMF until you put that EMF under a load, meaning you connect it to something. I'll give you an example. If you take a voltmeter and you measure the potential difference or the voltage across your car battery when it's just sitting in your driveway, pop the hood, put those probes on there, you'll probably get a reading somewhere around 13-ish volts, maybe even a little higher than that. Then if you have someone crank the ignition so that the starter motor puts a load on the battery, you're going to see that potential difference drop quite a bit. That terminal voltage will drop a considerable amount. It might get down to 11 volts, 11.5 volts. That's significant. That's due to the internal resistance. That car battery is a real EMF. And so when you were using the an EMF as a source of energy, as you would when you were trying to start your car, the terminal voltage V, so that's what I'm going to call the terminal voltage V, okay, would be equal to the EMF. So the EMF is like the ideal, what that power source could provide, or the chemical reaction inside of that battery could provide, minus the current that's flowing through that device times that internal resistance. So you can see for an ideal EMF, that second term would just go away. That I times R would be gone. Remember, this is coming from this idea that V is equal to IR. That's Ohm's law there, right? We talked a little bit about that on our Google Meet the other day. Okay, so this is when we are using a battery as a source. And that current to that starter motor is pretty large, and so you actually get a pretty big dip from the ideal or like resting EMF to the terminal voltage that we measure when it is under load. Now, if you take, let's say you take your cell phone and you plug it in, instead of using your battery as a source, you are actually using it as a receiver, meaning it is receiving energy. When you charge your cell phone or charge your Chromebook, you are actually not charging it. You're not placing charge on it. You're reversing a chemical reaction. You're putting energy back in so that chemical reaction reverses itself so that it again can maintain the potential difference or the EMF that we need it to in order for those devices to function. So when we are charging a battery of any kind, we would actually have to apply a larger terminal voltage because instead of having our current moving this way. So in this case, when it is being used as a source, our current would be moving from our ground or our negative, and maybe I should specify that negative terminal of our battery here is going to be considered our 0 volts, our lowest point. And then the top of our battery, that's going to be our terminal voltage, or the difference between those two is called our terminal voltage, and the current is moving through in the same direction as the EMF, right? Now, if we are going to use this as a receiver, so let me pause for just a minute. I'm going to clean up my screen and I'll come right back. Okay, thank you. I'm back. When we take a look at our negative terminal of our battery, it's going to be at our low potential, our 0 volts. And then at the top of our battery, that'll be our positive terminal of our battery. And again, when we're using it as a source, our current is going to be moving in the same direction as our EMF is pointed. Now, if we use this as a receiver, so we're charging the battery, right? We're putting energy back in, our current flow is actually going to be in this direction. So our current will be moving in the opposite direction as our, when it is being used as a source. That should make sense, right? We're just doing the opposite. We're reversing. So our terminal voltage, again, I'm just going to use that different color, will still have to be our EMF, because our EMF, remember, is that set amount. But it is going to have to be added to our current times our internal resistance. So we actually have to apply a larger voltage across our terminals than the EMF itself in order to overcome the internal resistance within the EMF itself. Now let's take a look at an EMF in a circuit. So if we take a look at this very simple circuit, this outline right here is the outline of our battery itself. So you can see we have an EMF source inside, so that's this guy right here, and then we have that small amount of internal resistance. And then that real battery is connected to a resistor over here. Remember, we've talked about potentials as hills over and over and over again, right? So you can see those potentials put in a graph on the right-hand side here. So it basically goes around the loop. This diagram goes around the loop in a clockwise rotation starting at point A right here. So the potential at point A is close to that negative terminal of our battery. And remember, in our last slide, we said that that was our 0 volts, which is why that voltage is right here at 0. Right? And as we traverse the loop, that EMF, that source, provides that potential difference. It takes that charge and pumps it up to a high energy, which is this right here. So that high potential occurs right over that EMF, right in there. And then little wire within the circuit, we have no change in potential there. And then we have a small change in our potential, which is the resistance times, or the internal resistance of that EMF times the current that's moving through it, right? V is equal to IR. We'll get it, IR, okay? And then we continue around our loop, right? We continue around our loop this way. And I want you to notice that this wire right here, anywhere along this wire is all at the same potential. We're assuming that the wire has no resistance to it or very little negligible resistance so that the potential stays the same throughout that wire. And then we have another drop in energy. We have energy that's actually dissipated through the resistor. Also, that energy is dissipated in that internal resistance of our battery, and we'll talk a little bit more about that in just a moment. So we have, again, another drop in our potential. It goes down to our lowest value, back to zero, back to our low potential as we go around our circuit. If you think about this in terms of a hill analogy, if I go for a walk and I step out of my house, I go around the neighborhood, I go up some hills, I go down some hills, and I return back to my house, I am going to be at the same elevation that I started at. I end at that very same elevation. That's the same thing as you go around a loop. We're actually foreshadowing a little bit to Kirchhoff's loop rule, in that as you go around a circuit and you end at the same place where you begin and you go one way around your circuit, you're going to see that you will end at the same potential that you started at, or that difference in potential or the difference in elevation in a closed loop is zero. We also need to think about the energy that is dissipated in those resistors, right? That's the thing that I alluded to just a moment ago. So we're going to talk a little bit about power. So before I click to that next slide, what I would really like you to do is take a moment and I want you to review your definitions for power. So if you need to get out your old notes, your equation sheets, whatever, I want you to review your definition for power, and I'll be back in just a moment. All right, so our definition for power in an electrical sense is our current times our potential difference. Now, if we have an ohmic device, which from here on out, we're going to be dealing with primarily ohmic devices. So remember, an ohmic device is one whose resistance stays constant no matter what potential difference you put across it. You saw that in your V is equal to IR quick lab, that those devices, those resistors stayed the same over different potentials that were put upon it. Okay, so if we take a minute and look at these two equations, we can actually take this Ohm's law here, right? And we can substitute this in for our potential difference in our power equation. Again, this is only for ohmic devices. All right, so when we do that, we get this equation. So our power is going to be equal to our current squared times the resistance in our wires. Now, notice that this is going to be our power that's dissipated by a resistor, and this is important. So if we go back to this slide here, we had an internal resistance here, and we had this resistor. So if an EMF is providing an energy source, we should ask the question, where does that energy go, right? We know energy is conserved. Well, in this case, it's dissipated, and it's dissipated through those two resistors. Sometimes you actually can sense or feel that. You can feel them getting warm when you have a large current going through them, or if you were to put a couple of small light bulbs in a circuit, you can actually feel that warmth. You can feel that energy being transferred in a different way, right? It's no longer electrical, it's going to be thermal, or it might be even light. When we look at our equation here, this is power that's dissipated by a resistor. Now this R here could be the resistor that is external to this device, so it could be this guy out here, right? But it also could be our internal resistance. So this R could be internal resistance, right? The other idea that we can get out of this is we can ask what is the power that is provided to us by our EMF. And so the power that would be provided by our EMF would be our current through that EMF times the value of our EMF, right? Just our current times our potential. And again, that's going to be the power that's generated by our EMFs. Okay, so now that we have a good handle on EMFs, I want you to do some of those practices that I've shown you on or assigned to you on Google Classroom, and then we'll come back with some loop and junction rules in a little bit. Good luck.